Hello everyone and welcome to Control Systems Analysis and Design. I have a problem here that we've got a transfer function or a block diagram, however you want to look at it. And what we need to do is put it into state space, but then I'm going to take it one step further and I'm going to get the differential equation from this and get the differential equation from state space to show that they're both equal and to show both of those methods. So doing state space first, when you have a transfer function like this, it's actually pretty easy. x1 dot, x2 dot, x3 dot, x4 dot. Now if you don't normally line up your state space representation as a full vector and you just do something like x dot, you're going to want to do it like this in order to easily go into a differential equation from the state space. But if we set this up, what you can do is go ahead and just lay out everything times x, I'm going to call this one just plain x, plus whatever this may be, times u, and then we've got y is equal to whatever this is going to be, times x bar plus 0 u. And for this matrix, you always just basically put in a 0, or at least that's how I learned it. Your professor may do something differently, but usually this matrix is just 0. And in this method, that is how it ends up. So, filling in this first matrix, what you do is you have the denominator of this transfer function, and all you have to do is look at the transfer function. It's a fourth order, so you're going to have 4 parts in this matrix, a 4 by 4 matrix, and you just go negative reverse order of what these values are. So you go negative 100, negative 7, negative 10, negative 20. And that's all you got to do. So fairly easy there. And then what you have to do is on the off diagonal on the upper side, you put in 1s. And then you have your, oops, sorry, that's a 1. 1, 0, 0. So now you have your first E matrix. Now you go ahead, fill this one in. Well, you can just fill it in with the numerator, and since the numerator has no coefficient, it is going to be 0, 0, 0, 100 for the x0 basically. Alrighty, and now going down here, well, the output, again, you're kind of playing off this. You want this to come out as part of the output. So the first value is going to be 1, 0, 0, 0. So that you basically imagine if this was inverted or translated, what am I, the word I'm trying to think of, flipped on its side, and then multiplied by 100, it would the 100 multiply by this 1, and therefore it would come out up here when you're doing the output. So that's why this 1 goes right here. And then, of course, 0 is right there. So that's your state space representation for this transfer function, just reverse order. If you happen to have something in the numerator, then you would do reverse order down here also. So you could put in a 1 right here and put in 100 right there, but that's not really necessary. Alright, so now what I'm going to do is I'm going to take this and find the differential equation for this. And that's fairly easy because you have output over input. I'm not going to say of s or anything. This is equal then to, if you solve for c and r, setting it up like this, you should get 100 r is equal to d to the fourth c over dt plus 20 d to the third c over dt plus 10 d to the second c over dt plus 7 dc over dt plus 100 c. Okay, so that's our differential equation. We know that from going from this transfer function. But say you were just given the state space and you had to get the differential equation. How would you go about that? Well, what you have to do is set up all the factors that are used in here. You've got x1 dot to x4 dot. So you just line this up, and then you can imagine this as x1, x2, x3, x4. I like to use this as a label because this is the coefficient of this value for this, which you'll see here in just a second. So x4 dot is equal to negative 100 x1 minus 7 x2 minus 10 x3 minus 20 x4 plus 100 u. Right there. And this is kind of odd, but you can see how this works. You're just adding in 100u right there. So you go straight across, add 100u, bang, there you go. Okay, so now x3 dot is equal to x4 x2 dot is equal to x3, and then x1 dot is equal to x2. So x1 dot is equal to x1 double dot. So x3 would then equal x1 triple dot. And you can see how this would go on. So then x4 would equal x1, 1, 2, 3 quadruple dot. And you can see how it goes, because if x1 dot is equal to x2, then the derivative of x2 dot is just another derivative on x1. Why is that relevant? Well, here, if you go ahead and take this equation right here and rewrite it in a form that's a little handier, put all the x's on one side and u on the other side, you'll end up with 100 u is equal to 100 x1, leave it as is, taking all of these onto the other side, over here with x dot, and then subbing in for each one of these coefficients the value of x1. You've got 100 x1 plus 7 x1 dot plus 10 x1 double dot plus 20 x1 triple dot plus x quadruple dot. And if you consider these dots, this is d to the fourth x1 over dt plus 20 d to the third x1 all over dt plus 10 d squared x1 over dt plus 7 dx dt plus 100 x1. And if you can, is equal to 100 u, which is the input. So you look at this and you say, oh hey, this one and this one are exactly the same, just with different variables used. So that is how you get the differential equation from the state space. You basically just go across, take these rows, set them up as equations, and then solve for each one of these individual dots as basically a single, with respect to a single variable and multiple with multiple derivatives. So it's fairly easy, but if you ever have to go to state space to differential equation, that's how you do it.